today we're going to be talking about a little bit of geometry, maybe, the solid affine line. So let me start with a recap of what we've seen so far. So we had this category of solid abelian groups, which was a full subcategory of light condensed abelian group. And this was some kind of analog of complete non-Archimedean topological abelian groups. But it's kind of, from a formal perspective, easier to work with. It's an abelian category. In fact, it's an abelian category closed under limits, colimits, extensions, and many other things besides. And also we had this left adjoint called solidification. And there's a symmetric monoidal structure here, which you think of as a completed tensor product, and such that this completion functor is symmetric monoidal. The definition was in terms of this object P, which was kind of the free module on a null sequence. So the definition was that M is solid so the definition was that it's solid if this map from null sequences to null sequences given by identity minus shift is an isomorphism. Okay, so that's what we had last time. Now I want to start doing a little bit of geometry. So we're going to be modest and look at the affine line, which is actually the most important case. So about this P, so it turns out that this P, even before solidification, so P is a ring.
So there are two shifts one can look at, because you can shift one to the left or one to the right.
Yeah.
Or both is equivalent, or?
I want the one, no, I think only one is good. I mean, I want the one that's injective. So P is a ring, and maybe it'll be clarified in a sec, maybe. Well, P is a ring, and in fact there's a ring map. So from the polynomial ring in one variable to P, and the shift is multiplication by T. So that's what you have before solidification, but after solidification something extremely nice happens. So when we solidify, well, we actually already explained what the free module on P is. So there's a compact projective generator here, which was a countable product of copies of Z. That's kind of the basic object from which everything is built. And you can get that object just by solidifying this basic sequence space P. And if you take into account the ring structure, what happens when you solidify is you just get the power series ring in one variable. So in the solid context, the universal carrier of a null sequence is just this power series ring. But moreover, there's a very nice property of this situation. So lemma.
How do you multiply things in P that looks like a quotient by something which is not, the null sequences is like a ring without unit usually.
Yeah, so let me explain how you get the ring structure just very briefly. So it's better to think of this construction as being attached to n rather than n union infinity. So more generally, if you have a set, say, or any countable set, you can define measures on it as the free module on any compactification modulo the free module on the boundary, and it's independent of the compactification, and it's functorial for proper maps. So now, and it's symmetric monoidal. You can see that using independence of the compactification. If you take the product of two countable sets, then measures on one tensor measures on the other is measures on the product. So using that and the fact that addition on the natural numbers is a proper map, it has finite fibers, you can see that addition on natural numbers induces this ring structure on P. All right. It's the same, and addition on natural numbers also in some sense induces this. So that's why, yeah. All right. So the lemma is that, so if you do the tensoring in the solid world of this power series ring with itself over the polynomial ring, you just get the power series ring again. Or maybe the multiplication map is an isomorphism, you could say, and even the derived tensor product. And well, this is quite elementary because we know how to. We know how to do tensor products in solid Z. Peter gave lots of examples of calculations in this category. And the tensor product of two of these basic guys is just another one of them. And so if you do, so the proof, if you do Z power series T, let's say T1 tensor over solid Z, Z power series T2, that's just Z power series T1, T2 by the basic calculation of the solid tensor product. And then if you want to get to this, you just do modding out by, you just identify the two different variables, T1 minus T2. And power series ring modulo T1, T2 is the power series ring in one variable. There's maybe another perspective. Peter also mentioned this fact that if you take the solid tensor product of two derived complete things, then the result is still derived complete. So, well, maybe you have to worry a little bit about this, but morally, if you want to check this is an isomorphism, both sides are derived T complete, you can check it modulo T, and modulo T, it's really a triviality. So kind of, okay.
So the derived solid tensor product, is it defined as the derived tensor product, then you solidify, or is it, how is it defined exactly?
Yeah, it's the, you can either say it's the left derived functor of the solid tensor product, or you can say that you take the derived tensor product and then derived solidify it. It's all the same.
And do you need to know there are somehow enough flat things to construct the
You don't need to know that, but it is actually true that all of these guys are flat. I don't know if did Peter mention that? I forget. Yeah. Okay. Yeah, so a priori you'd need to resolve both variables, but since you have flat objects, you would only need to resolve one. Okay, so what is the interpretation of this? So this corresponds to sort of the affine line, you could say. And then since this satisfies this idempotence property, sort of like when you invert an element in a ring, you kind of get the same thing. You can think of this as corresponding to some subspace. Of the affine line. So a subspace as opposed to just a random space with a map to the affine line. That's the interpretation of this idempotency. So then you could ask, okay, how should one think of this subspace? What subspace is this? So the naive thing to say would be that it's the formal completion of the affine line at the origin. Well, because it's a power series ring. But that naive interpretation is not the correct one. And so this does not correspond to a formal neighborhood of 0 in A1. And the reason is that interpretation is not stable under base change. So look at base change. By which I mean this is all implicitly over Z, but we could tensor it to any ring or any solid ring and see what pops up. And let me do a little calculation. So let's base change to a non-Archimedean field. Say, I'll just take the simplest example, QP, and we'll see what pops up. So we take the affine line over QP. Oh, sorry. Well, maybe I'll just say, yeah. We take QP, and then we do a solid tensor product with this thing here, and we want to compare this to QPT. So QP is ZP with P inverted, and the solid tensor product commutes with colimits in both variables. So this is the same thing as ZP, solid tensor product, Z power series T, and then you invert P. But this ZP has a resolution by 2 copies of, so ZU, maybe mod U minus P. It has a resolution by 2 copies of this power series ring. So we know how to do these tensor products, and it just does the naive thing of you can pull in the limits. So the result of that is that you get ZP power series T, and then invert P on the outside, which is not the same thing as the formal completion at the origin, namely QP power series T. So it's contained in there, and it's the subset where the coefficients are bounded in p-adic norm. So what is the interpretation then of this ring? This ring is the ring of functions on the open unit disk in A1 over QP. So if you could ask, if you take, say, maybe after an arbitrary non-Archimedean field extension of QP, you could ask, when you plug in a value in that field, when will such a series converge? And the answer is it will converge if and only if the number you plug in has absolute value strictly less than 1.
Ring of bounded functions, actually.
What's that?
It's the ring of bounded holomorphic function of the open unit.
Ah, yes. What?
Not the full, because sometimes...
Yeah, there's another one.
Ah, that's true. Yeah, that's the bounded. Thank you. Yeah, yeah, that's right.
Sometimes people use the not necessarily like the Rober ring and stuff, which is not bound. I don't know, there are all kinds of rings.
Yeah.
I don't know what...
Well, okay. Certainly, all these functions converge on the open unit disk, but they don't converge past that. So then the interpretation that this suggests is that this ZT, this should be thought of as corresponding to some sort of open unit disk. And it's just that over a discrete ring like Z, you can't tell the difference between the open unit disk and the formal completion at the origin, but the difference pops out when you make a base change to something that has more freedom to play with. Okay? But in rigid geometry, it's not really the open unit disk that's fundamental, usually. It's the closed unit disk. So what about the closed unit disk? Well, one way to understand the closed unit disk, if you understand what an open unit disk is, you can imagine putting the open unit disk at infinity instead. So then you're looking at, then you get the complement of the closed unit disk. And then that's one way of talking about the, the complement of the, you get the complement of the closed unit disk. And the complement of a thing is just as good as describing the thing. So let's take this guy and put it at infinity instead. So the complement, well, this is all just at the level of loose thinking. So we can take this power series ring in one variable, and we can tensor it over, well, but let me call the variable t inverse instead, because I want to be thinking of putting it at infinity. And then I tensor over zt inverse with zt t inverse. So then I'm puncturing at infinity so that I actually live in the affine line. So I have a homomorphism from zt. And what is this ring? Well, I'm just taking this power series ring and I'm inverting the variable there. So another way of describing this is as z power series in T inverse. So that's the open unit disk centered at infinity. So if we want to understand the closed unit disk, we should in some sense be kind of localizing away from this complement. Or another way of saying that is that we should be killing this object. So to get we need to kill this thing here. So I'm just going to make just a preliminary. So this z power series T inverse is a module over zt as I just exhibited. And it also has a very simple resolution. So note, zt inverse, we can think of that as, let's disambiguate and call the variable u. We can think of it as z power series u and then invert u. But one way to invert u is to adjoin the thing that you want to be the generator, that want to be the inverse, and then enforce the equation that says that they're inverse to each other. And when you look at it like this, I'll rewrite that. So we get zt inverse has a two-term resolution where you have z power series u bracket t and z power series u bracket t. And here you have ut minus 1. So two-term resolution. And what are these objects? Well, these are just the base changes of our fundamental p, not to solid z, but to solid z, and then adjoin a variable t. So these are resolutions by the compact projective generator of the category of z bracket t modules in solid abelian groups. So killing this thing should be the same thing as requesting this map to become an isomorphism. And now this suggests the following, based on an analogy with the definition of solid up there. So definition. So let's say we have one of these guys. Let's say that is zt solid. If and only if when you take internal Hom from P to M, and then internal Hom from P to M. And then you take the map, which is given by, so now U corresponds to the shift, and T is the extra thing we have acting on M, because M is a Z bracket T module. So we have shift times T minus 1. We want this map to be an isomorphism. And then this note up here is saying that that's the same thing as requesting that if, now I should maybe pass to Arham. It's the same thing as requesting that there are no Arhams from this object we're trying to kill into M. Okay. So now, theorem is basically that this definition, the name is well chosen, so that this ZT solid theory over ZT is very similar to the solid Z theory over Z. So let's say and we can even, I mean, everything is also inside condensed. Light. This is an abelian category closed under limits and colimits, extensions. So if M is an arbitrary, say, condensed ZT module, then internal X, and N is in solid Z, ZT, then internal X over ZT from M to N is also in solid ZT. There exists left adjoint to the inclusion. Call it, let's say, well, I'm going to at least temporarily denote it by upper T solid. We're forcing the variable T to be solid, you could say. So that's.
Sorry. Mod ZT cond Z and cond ZT is the same thing? The one you wrote in the first?
Yes, I used different notation. Yeah, sorry. Yeah, this is supposed to be the same as this. Yeah. There exists symmetric monoidal structure on this derived solidification over ZT. And then the derived analog holds as well. So the derived analogs of all these claims hold, and moreover, the derived theory is naive in the sense that an object in the derived category is derived solid if and only if each homology group is solid in the sense of the abelian category. And it is the derived category of the abelian category. Okay, so that's all the kind of formal stuff. But that in the solid Z theory, it was also important to understand what was going on. It was important to understand the basic compact projective generator, which is always gotten by just solidifying the sequence space. So let me make a claim about that. So if you take Z power series, maybe I'll say, let's not think of it as a ring, we're thinking of it as a module now. So if you take a product of copies of Z, you base change it to Z bracket T, and then you solidify, you get, a product of copies of Z bracket T. So maybe a little remark about an interpretation of this. So I said solid Z was kind of analogous to complete non-Archimedean topological abelian groups. Non-Archimedean means, say by definition, that there's a basis of neighborhoods of the identity consisting of abelian subgroups. So what would be the analogous interpretation of solid ZT? It would be that you have a complete non-Archimedean thing where, moreover, there's a basis of neighborhoods consisting of ZT submodules. And you can think of, and for a basic example of a ZT module which is non-Archimedean but does not satisfy that property, you can think of this ring. You can not find a basis of neighborhoods of 0 which are stable under multiplication by T because they're stable under multiplication by T inverse instead. And so, but in some sense, the theorem is that if you kill just that one guy, then you've explained the difference between the two notions. Okay. So
in the previous theory without light, it was a little bit different. It was not defined using this P, but
well,
okay.
it basically was done this way. I mean, maybe we didn't make this explicit, and we maybe more talked about just this, but we definitely talked about this. Yeah. But it does make it more clear to think of it that way with the P. Okay, so the proof. Yes?
I'm a bit confused about whether ZT itself is ZT solid.
So it is. That's part of the theorem, because I'm claiming in particular that this is ZT solid, and ZT is a retract of this. So it's something that we need to prove, and we will prove it.
But it's not solid.
What?
ZT is not solid, right?
ZT? Oh, no, it is. So as an abelian group, you mean? Or?
Yes.
No, every discrete abelian group is solid because it's generated under colimits by Z. No, it's an important point. Thank you for bringing it up. Yeah. Other questions? Okay.
And then ZT power series is also solid.
The ZT power series is also solid, yes. Because it's a limit of things. I mean, you can build it from limits and colimits from ZT, so it's, yeah. All right. So for the proof, all of these properties, so all except the last, that's exactly the same. The arguments for all of those things were completely formal, just based on the fact that you have this internally projective object P, and you're asking that some endomorphism of internal Homs from P to M become an isomorphism. That was all that Peter used when he was proving the analogs of these claims for solid Z. So the fact that we have a good formal theory is already contained in there. And then in Peter's lecture, the hard part was identifying the free modules, that when you solidify this sequence space P, that you actually just get a product of copies of Z. It fills up the whole thing. Thankfully, so that part is actually going to be easier here, because we already have solid Z. And basically thanks to this interpretation of killing some object. So the claim, the key claim is that that you can give an explicit formula for this derived solidification. So I apologize for the janky notation. Now this looks really bad. Derived solidification with respect to T. So that this is just an internal R Hom over Z bracket T from the quotient of this ring by this ring to M. And note that this does have the required map from M because M is R Hom over, minus 1. Shift by minus 1.
So I'm just trying to read what that last thing says. That's MT squared.
Yeah, L. So derived solidification. Yeah, the derived functor of this thing here. Yeah. Which I kind of prefer actually to think of as just the derived analog of it.
And the Arom underline is either in all condensed or only in solid? Or?
It's the same. So basically because of this. So, I mean, the derived.
So when you compute, of course, you have Grothendieck categories, so you have a well-defined, even with unbounded complexes. But how do you check exactly? I think Peter must have briefly said that. I don't remember, but how do you check that the Arom or Arom underline are the same for? Maybe there is some adjunction argument. I don't remember exactly.
I mean, you basically, I don't know. Like I said, I sort of tend to think on the derived level from the beginning, but the basic point is that everything has a resolution by these internally projective guys, and then on those they're the same, and then it's some derived limit of that, and it's just
internally projective in all condensed. Or
in light condensed. I mean, so but it's really not. That's really not necessary either. I mean, this also works in all condensed. So, I mean, I claim it's formal, and I also claim I don't want to get into the detail right now. So, yeah. So let's maybe discuss after if you still have questions. Okay. Right. So the proof of claim. So this follows formally from the fact that this ring Z power series T inverse is idempotent over ZT, which follows from the very first description I gave of it as the base change of the. We check that the power series ring is idempotent, and we put that at infinity, and the idempotency is preserved. So, for example, the idempotency of that, so what is this thing here? It's just the homotopy fiber of the inclusion of this into this, and this is the base ring. And you can easily check that this idempotency is equivalent to the derived idempotency of this object, and that means that if you take this expression and you apply it again, you get the same thing back. So that's kind of an idempotent operation. And again, the same idempotence will prove to you that if you take this operation and you arhom from this guy, you get 0. So this thing is ZT solid. And that's not quite everything you need to check, but it's basically everything you need to check. It's an idempotent operation, and M is solid if and only if this map is an isomorphism. So it's just completely formal, and I won't write out all of the details. So maybe I'll just say note. So this, yeah. Okay. So that's a formula for the derived solidification of a general Z bracket T module, but something nice happens if your Z bracket T, so we still haven't proved the claim, but something nice happens if your Z bracket T module is base changed from a solid Z module. So next claim is that the functor from the sort of pullback functor from solid Z to solid ZT, so sending a module M to, you take M tensor Z ZT, and then you solidify. This functor is T exact, preserves limits and colimits, and it sends Z to Z to ZT. So if we prove this, then we in particular get this claim, because this is that functor applied to product of copies of Z. I claim the functor commutes with products, so then we could just try to it's enough to understand what happens with Z, but I already also claimed that Z goes to ZT, so we'd be done. So the proof, So we just take this formula for the solidification, and we plug in the case where M is also induced. So we get that, so M tensor ZT LT solid, this is the same thing as I'll just write it M brackets T. By that I mean M tensor Z brackets T. And now we're computing an RHOM over ZT. So the way to do that is to disambiguate the two occurrences of T and then equalize them at the end. So that's calculated. So let's say Z power series U. Well, this is so U Z power series U. So two-term complex, I'll write it vertically, so to speak. So then you equalize U and T, or no, sorry, U and T inverse? No. Or sorry, no, let me say I should say rather that we equalize T and the shift operator on here, which is induced by multiplication by T here. So let's denote that by shift here. And then I'm switching variables from T to U. Okay. But note that now we're taking RHOMs in solid Z, but this is one of our compact projective guys. So RHOMing out of that commutes with colimits, and this MT is a colimit. It's just, so we can put that out here, like this. And then we're taking this thing, bracket T, and we're modding out by T minus something. So that means that, or we're not modding out by it. That modding out would be the cofiber. We're doing the fiber instead. But we also had a shift, and those two actually cancel. And in the end, what you get is that this is RHOM over Z from U, Z, power series U to M. And that's the key formula. Oops. And we've kind of, along the way, we sort of lost the ZT module structure on this thing. But you can recover it. It's induced by, so the multiplication by T is here given by sending U to 0, U squared to U, U cubed to U squared, etc. So if you do that there, then that induces an endomorphism here, and that's the multiplication by T on this resulting thing.
Sorry, I missed what you said. So what is isomorphic to this green?
This is a bit a somewhat silly notation. Is homotopy fiber of this map, or some kind of shift of a mapping cone, and that's the same as this, and it's also the same as this. Okay, and now we're done. Now this functor. Again, this is internally projective in solid Z. So this functor is T exact, and it preserves limits and colimits in solid Z, but limits and colimits in solid ZT are calculated on the underlying level, because it's just part of a module category. And then the last claim is that Z goes to just the usual polynomial ring in one variable. But what happens when you plug in Z here? You're taking RHOMs from this product of copies of Z to Z. It turns into a direct sum of copies of Z. And you can check that what you get is just the usual Z bracket T, even with the ZT module structure. Or really, there's a natural comparison map, which you see to be an isomorphism. Okay?
So there was this someone proved, it's not related directly to the theory, but someone proved just on abstract abelian group that home from a product, infinite product of copies of Z to Z is a direct sum. But this is not, here you are doing it in...
This is easier. This is easier.
This is formal.
Yeah,
The other
yeah.
one is not.
Yeah, yeah. Okay. So we can also do other examples of such a thing. So let's do another example. So that finishes the proof of the theorem. So we now have a grip on this solid ZT theory. And I want to advance the interpretation that the solid ZT theory is like working over the ZT without the solidification is like the affine line, and ZT with the solidification is like the closed unit disk. That was kind of the interpretation that I started with. But let's do an example. Again, in non-Archimedean, let's base change to a non-Archimedean field and see what happens. So let's take another example in above. So let's look at QP T, so that's functions on the affine line, and now we want to restrict to the closed unit disk in the sense that we've just described. So we take the T solidification of this. So this is an instance of this functor here, and I just said this functor has all the properties in the world, so it commutes with colimits, so I can, again, take the T to the outside. The 1 over p to the outside, and it also commutes with limits, so I can take the p-adic, so I can take limit over n of z mod p to the nz bracket t, t solidified, and then 1 over p at the end. And now we're applying this functor there to z mod p to the n, but that's just 2 copies of z, so you get the same answer as for z, it's just discrete. So this is just inverse limit over n of z mod p to the nz bracket t, 1 over p. Or in other words, it's zt p completed, 1 over p. And these are the functions on the closed unit disk. Kind of as desired. Okay, so maybe I'll take a 5-minute break. Maybe I forgot to give the interpretation of the coefficients here. So again, this is some power series with coefficients in QP, but here the coefficients tend to 0 p-adically. So it's a smaller ring of functions, so it converges on a bigger region. And you're allowed to be now on the boundary, so to speak. I mean, yeah. Okay, now let's play a fun game. So I've been talking about the open unit disk and the closed unit disk. Or maybe I'll say, or the closed unit disk and the complement of the closed unit disk. But it's kind of, there's always this fun question of what exactly is open and what exactly is closed. Because in rigid geometry, the closed unit disk is considered as open. And the open unit disk, well, I suppose it's also open in a sense, but it's not quasi-compact. So let's play a game.
Also, you can use the Berkovich viewpoint, which interchanges somehow. It has another way, then it is closed and not well.
Yeah, so I claim that our formalism is going to give a definite answer to this question. What's open and what's closed? Yeah. Okay, well, all right. Where was I? Oh yeah, what's closed and what's open? So let's take a look at the categories, you could say, we've attached to the various geometric objects. So for the affine line, we said we're just thinking of it as the polynomial ring in one variable, but then the linear algebra category is just ZT modules in solid abelian groups. And let me actually go to the derived perspective. So but then inside there we had this derived solid. So we had D of solid ZT. But actually it's better to think of that as a quotient really, because the symmetric monoidal functor is the derived solidification functor, which goes like this. So, but then on the other hand, we had the complement, and the complement was the open unit disk, or rather the open unit disk moved to infinity, so that's this thing, and that corresponds to D mod Laurent series in T inverse solid Z.
I think someone asked before, but I forgot that you had the solidification, which is one adjoint, or should be another adjoint on the other side?
Wait. So then, and then this is just the natural include. Well, it's a forgetful functor a priori. You're forgetting the extra module structure, but it's in fact a fully faithful inclusion because of the idempotency. The idempotency of this thing means that there's at most one ZT module structure on any Z Laurent series T inverse module structure on any ZT module. So this is actually like a localization sequence or what have you. So this is the symmetric monoidal quotient of this by this thing, which is kind of an ideal in there. And what kind of adjoints do we have? And which of them are well behaved and so on. So, well, we know that this one has a right adjoint, which is given by the inclusion. But it also has a left adjoint. And the left adjoint is given by sending M to, I guess, the fiber. So you take M and then you base change it to infinity. And you take that cone diagram here. So it's the fiber of M mapping to M tensor over ZT with the Z Laurent series T inverse. So, and this left adjoint is in a sense better behaved than the right adjoint, the naive inclusion. And by the measurement that it's better behaved, well, they both commute with colimits, but this one satisfies a projection formula with respect to this fundamental functor, which is the symmetric monoidal functor. So this left adjoint is kind of linear over these two symmetric monoidal categories. So this is better. So, and I'm going to call this one J upper star, and this one J lower shriek, and this one J lower star, this inclusion here. And on the other hand, for here, we have this functor here, which I'll call I lower star, the inclusion there. So it has a left adjoint, also I upper star, which is just the base change functor, which is symmetric monoidal. So that's kind of the more fundamental one from this perspective. But it also has a right adjoint, I upper shriek, which is given by some Arham. But it's less well behaved again, because here this one satisfies a projection formula with respect to this one. So this is a linear, this functor is linear over this symmetric monoidal category, just like this functor is linear over this symmetric monoidal category. So
J lower star as an adjoint, the inclusion as an adjoint on the other.
it does, but that one we don't talk about. Yeah.
Now this was the question I recall.
Yeah. Because already this one's not as nice as, I mean, the good adjoint is actually up here. So, so the interpretation that this suggests, so this is exactly like if you have a topological space X, and then you have Z a closed subset, and then U the complement open, then you get, if you have on derived categories of sheaves, you have exactly the same thing where you have the open over here, you have this thing satisfies a projection formula. You happen to have this other guy, but it's not as well behaved. And then you have I lower star from D sheaves Z. Z, I upper star, and then I upper shriek. So it's satisfied, formally speaking, it behaves exactly the same way. And actually, they're both special cases of the same thing, which is you have a symmetric monoidal category, and you have an idempotent algebra in it, and it generates the whole situation. In this case, you have this category and this idempotent algebra. Here you have this category, and then the push forward of the structure sheaf from the closed push forward of the constant sheaf from the closed subset, and completely analogous formalisms. So that tells us that, from our perspective, the closed unit disk should definitely be thought of as open, and the open unit disk should definitely be thought of as closed. So as far as I'm concerned, the question is settled. But also, this another funny thing is that if you think about this perspective, it's also telling you that Zariski opens in usual algebraic geometry should be thought of as closed. And I think that's also true. I can explain why if people want to know. All right.
But not for usual.
You don't like
Oh, no, you start from the usual theory of like patching of sheaves, which like is used in many contexts, like in Fesoper. I mean, it was used, but then for usual, it is used for the usual topology, like the risky of a Tal or Analytic. But then you somehow develop it further and decide that now that the risky opens are close to this.
I think I'd like to try to convince you, but not right now. All right. Sorry?
Which idempotent thing comes from the risky open?
I don't understand the question. No, I heard the question. I don't understand it.
What? Because you said the closed things correspond to an idempotent object in a symmetric monoidal category.
Yeah.
So you said that the Zariski open is like closed?
Yeah, yeah. So for example, distinguished open is just the ring with the function inverted. That's idempotent. Yeah. Yeah. So, I mean, it's so maybe I should say quasi-compact opens are closed. It's probably, yeah.
The derived direct image of the structure sheaf is idempotent?
Yeah. Okay. All right, so now, yeah, so this, by the way, this, yeah, so this, we're kind of going to be guided by this sort of thing in setting up the definition of analytic stack and so on, like the idea of, so one of the things we discovered is that when you move to this condensed, solid, whatever context, that you actually get 6 functor formalisms in large generality on derived categories of, so to speak, quasi-coherent sheaves. And they have, I mean, they really have nice interpretations. So for example, if you think of this thing as being what sits at infinity, then it makes sense that this is extension by 0 because you're taking your sections and then you're killing the ones that live near the boundary. And it really all just plays quite nicely. And we showed how to give proofs of things like Serre duality and so on using these formalisms. And so we take this perspective seriously that the derived categories and the functors between them are going to dictate to us what the geometry looks like. There's another thing I remembered in the break that I forgot to mention is that, so I said that this is T-exact and preserves limits and colimits, but I want to caution you that this T solidification from solid ZT is not T-exact, but it's only, so it's only off by 1. So yeah. I said it was given by R-Hamming from this object, which has a 2-term compact resolution. So it's only off by 1 from being T-exact. So it sends, everything connective goes to something connective. Everything anti-connective goes to something that's at most a 1 shift of something anti-connective. So it's not, derives, T solidification is not exactly exact, but it's very controlled.
But the composed map is?
Yes, exactly.
So the first map is T-exact and the composed map, and the second map is not exact.
That's right. Yes, it's a bit funny. All right. Okay, so now I'm going to say something like, I want to motivate what I'm going to do in the rest of, So I'll say vista. So what is one place where probably going to go is, so we want to look at solid rings. So i.e. commutative algebra objects in this tensor category, solid Z. And then we want to see, so generalizing our discussion when R is Z bracket T, we want to see some subsets, like closed unit disks, open unit disks, things like this. But of course, when you have a big algebra, you'll get many more such subsets, and we want to organize what you see in a nice way. And it's not necessarily the most general thing you can do, but what we're going to do basically is just take the things you see over Z bracket T and kind of base change them along all possible maps from ZT to R. That is, all possible functions in R. And what we're going to end up with is the statement this derived category of mod R solid Z, even this tensor category, localizes along the valuative spectrum, the spectrum of all valuations of, well, the underlying usual commutative ring of this solid commutative ring.
Localizes. So you take the valuative spectrum of R, just of R viewed as
a discrete ring, yeah.
As a discrete ring, yeah. And the valuative spectrum is, okay, it's like a residue field and evaluation without, the valuation doesn't have to be integral on R, it's just any evaluation.
Yes, that's right. So
it's a big, which is, and it has the topology, which is, okay, I know the topology, but it's kind of, it is topology which induces the topology on things like SPA and so on.
Yeah.
But it's kind of, because sometimes one gets maps which are not spectral in this. Okay, but okay, it's possible to consider it.
So it's, it's possible to consider it indeed, and it's, a priori more general. Okay, and so I won't remind you what evaluation is right now, but I will remind you that this space is similar to the usual spectrum of a commutative ring in that it has a basis of quasi-compact opens. It's a spectral space. And it even has a particularly nice basis, which is in some sense analogous to the distinguished affine opens in algebraic geometry. And while a distinguished affine open in algebraic geometry is parametrized by a single element of the ring, here you kind of have to take a little bit more data. So the basic opens are the so-called rational opens. So X, you have to take finitely many functions, and then you form this thing here where the interpretation is that you invert G, so we're inside the Zariski distinguished open for G, but then we shrink further by requiring that the sort of F1 be, the absolute value of F1 be less than or equal to the absolute value of G, the absolute value of F2. All of the absolute values of these guys should be less than or equal to the absolute value of G.
And G should be non-zero.
Yes, that's what I said. Yeah, G, yeah. So right. And so I'm saying that this localizes on this, meaning you have actually a sheaf of categories, a sheaf of symmetric monodal categories. And what you're going to attach to this thing is a version of the solid theory, So you look at those M in D mod R solid Z, such that, well, first you want to say that multiplication by G on M is an isomorphism. And second, you want to say that if you take this internal Homs from P to M, and internal Homs from P to M, and you take Fi times shift minus 1, this should be an isomorphism for all I. So you can, or in other words, Fi over G, sorry. So in other words, so you think of all of these guys as maps from, say, spec R, so to speak, to the affine line. Then you want that G lands in the standard, Zariski non-zero locus, and you want that the Fi over G land inside the closed unit disk. So. Okay, so I'm not going to go into details about that, but where should I go now? I don't know. Maybe here.
This notation as BP just refers to the locale corresponding to this insoluble something.
I mean, yeah, I don't, you can think of it as a locale, but it's also a topological space. Yeah. And the points have a nice description and so on. Okay, so what do I want to do today? Well, or maybe partly do today. So in particular, so I'm claiming this category localizes along this space. And in particular, you get a structure sheaf. On the space. And what I want to do in the next bit, so goal for rest of lecture, is make this this structure sheaf explicit and compare, well, maybe probably start to compare it to Huber's theory. So we're eventually going to produce this data by very easy formal means, but it requires some language and setup, so we can't do it yet. But I want to make at least this part of it explicit already at the beginning. Okay. So let's see. So let me make a, let's start with this generality. So we have a solid ring. And let's take an element F in R, or really I should say in the underlying discrete ring of R in case there's ambiguity. And that in particular, well, that gives you a map from ZT to R, which sends T to F. And then we can sort of see how these loci that we've identified can be correspond to properties of R. So let me make a definition. F is topologically nilpotent if this map factors through, this homomorphism, I should say, factors through the power series ring. And F is power bounded well, I want to say that if this map, well, the map geometrically factors through the closed unit disk, but the way to say that is let's say if R is actually, so R is an algebra over ZT. In particular, it's a module over ZT, and we can ask that it be solid.
In the first definition, the factorization is unique.
Yes, it's unique if it exists because of this idempotency. So that's an interesting fact, actually. This is also the free module on a null sequence. And so So even though there are sort of solid abelian groups that have like non-Hausdorff behavior, still kind of this limit is unique if it exists. Okay. So basically in the definition of solid, you're imposing that certain limits exist uniquely, even though you have non-Hausdorff behavior. Okay, so that's the same thing as saying that if you take Hom from P to R, Hom P to R, F times shift minus identity, that this is an isomorphism. I was just, oh, someone's talking. Hello, yes. Yes.
The first condition literally equivalent to saying that there is a null sequence which is the powers of f and then 0. So it's literally topological.
Yeah, it's, I mean, I was going to explain the relation with classical definitions, but it's quite immediate for this one that it's the same as the classical definition. So maybe I'll just repeat what Peter said. So this is the same thing as this P thing solidified. So yeah, this map sends T to F, but it's a ring homomorphism, so it sends T to the N to F to the N. And then saying that that factors through P is the same thing as saying that this sequence, so 1 F, F squared, so on, extends to a null sequence, which is basically exactly the same thing as being topologically nilpotent. Yeah, the new phenomenon in the solid case is that it's unique if it exists, such a limit. That's kind of fun. Okay.
It factors through in the sense of rings or in the sense for the uniqueness of the factorization. Okay, you can ask factorization as a condensed abelian group or...
In the sense of rings, yeah.
So you could have another factorization just in the sense of condensed.
Yes, that's true, yeah. Yeah, I was maybe being too imprecise earlier, thank you, yeah.
Or in the sense of ZT modules is enough, or I'm not sure.
I don't think so. So yeah, thank you for the comment. Yeah, just as rings. Okay. Right. So here's a lemma giving basic properties. Sorry. Let me say. So we write R0. So this is again, it's kind of standard notation in Huber's theory. So it's a set of power-bounded elements. And R00, set of topologically nilpotent elements.
Which is a subset.
Well, yeah, I'm going to prove that. Yeah, so lemma is that R0 inside this ring here is an integrally closed subring. And R00, first of all, is contained in R0, and it is a radical ideal.
So I'm still confused
Yes.
about this null sequence.
Okay.
If you have something which is a null sequence in just the sense that the map extends to a null sequence, then you don't know that it factors as a ring, that this is a ring map.
That seems correct to me, yes.
Okay, so doesn't mean it's topologically important in your definition, in your sense.
But on the other hand, maybe, yeah, no. I mean, yeah, you're right. Yeah. Well, it's the same. Okay, that's a good point. But if you have something that comes from a Hausdorff topological ring, for example, if the target is quasi-separated, then independently of asking about the algebra structures, then the limit is unique if it exists. So, yeah. Oh, quasi-separated was this analog of Hausdorff in the condensed setting. So still, if you start with, yeah.
Then it is automatically a ring map if it exists.
Yes, because of density, basically. Yeah.
Okay, so we are not sure whether topologically important in the null sequence sense is always the same as this.
Well, okay. I mean, Hausdorff. I mean, yeah. All right. So, well, hello. Okay, so proof. So why is this a subring? Well, I guess maybe the first thing to check is that it has a unit. That's part of what I mean by subring. But if you look at it, that's the definition of solid. That's one way of saying it. So you put f equals 1 here. Okay. Okay, now I want to show that if f and g are in there, I'll prove that it's a subring by showing that any polynomial, so if f is a that if you apply any polynomial to f and g, then you're still in there. So how can we do this? So kind of, maybe there's different ways of doing it, but I think the cleverest one is maybe, so we can look at the map from the polynomial ring in two generators to R, which sends x to f and y to g. And our hypothesis is that R is a solid zx module and it's a solid zy module. And what we want to conclude is that for any map here from the polynomial ring in one generator T, that R is a solid ZT module. Okay? So we can, so first resolve R by, it's a solid, it's definitely solid as an abelian group. So we can resolve R by these guys. We can make a resolution of R by direct sums of our compact projective generators. But we know that R is z bracket x solid. So if we solidify, if we solidify with respect to x, then what does this turn into? It turns into direct sum. Sorry. R is also a. I'm sorry. I'm sorry. I should give myself my variables, x and y, because R was also a module over z bracket x y. And now I solidify with respect to x, and I get direct sum of product of copies of z bracket x bracket y's by the properties of derived solidification that I proved earlier. But then, and then it doesn't change R, so that's still a resolution of R. And then we solidify with respect to y, and we get a direct sum of product of copies of z bracket x y, again by the same reasoning. So in total, we see that R can be resolved by these guys. But each of these is clearly, solid over ZT because it's a limit, it's a co-limit of limits of things which are solid over ZT. This is solid over ZT because it's discrete. And then this is a product, and that's a direct sum. So in total, it's solid over ZT. Okay? So I didn't directly use the definition of solid. Instead, I used the description of these generators. So, right. Now, how about showing that R, the topologically nilpotent elements are all power bounded? You can use a very similar argument. So what we have is a map from Z power series x to R, which sends x to f, which means that R becomes a Z power series x module. So now if we resolve R by direct sums of products of copies of Z, we're allowed to tensor this with Z power series T. But we know how to compute this tensor product. They're both just products of copies of Z. So this is direct sum of product of copies of Z power series T. And this is also solid over ZT already. So we conclude that R is solid over ZX. T. I switched to T somehow. I switched to X somehow. So we conclude that this composition, R is actually solid as a ZT module. Oh, I didn't prove. Oh, I forgot to prove it's integrally closed. Oh, I'm sorry. Let's do that. So it's again a very similar argument. So let's say that we have an equation of the form so where all Ci are power bounded. So again, we just make the universal things. We have Z bracket x0 up to xn minus 1. And over that, we have the ring where you adjoin another variable. Let's call it T. And then you set the equation. And we have our solid ring R. And by hypothesis, we have a map here such that when we compose to here, R becomes a solid module over each of the variables. And what we want to show is that when you compose here, it becomes a solid module over this variable. So I'll just say it quickly in words. You use the same trick. So you resolve R first as just a Z x0 up to xn minus 1 module in solid abelian groups that you solidify with respect to each of the variables. You find yourself built out of product of copies of this ring. But you're also a module over this, so you can tensor up to this. But that's a finite free module over that ring. So then that will just go inside the products. And you'll find that you're resolved by a direct sum of products of copies of these guys. And then because this individually is solid and solid is closed under limits and co-limits, you deduce that that's solid as well. So the key here is just that this is finite as a module over this, so that tensoring with it you can bring inside the product. Finite free, yeah. Although, well, that's not really necessary. The ring's Noetherian and you can resolve. Yeah, finite would be enough, in fact. Yeah.
You mean finite with all with representation by finite?
Well, it's an Noetherian ring, I mean, yeah. Okay. And the rest, so, yeah. I mean, I'll leave the rest to you. It's completely analogous arguments, like why it's an ideal and why it's a radical ideal even. So fun exercises in that style of argument. So so now we can describe this structure sheaf. So now suppose we have, again, a solid ring. And then we have G and F1, G, comma, F1, comma, Fn in R solid. Then the claim is that, well, yeah, so now, yeah, so there exists a universal, an initial solid ring. And I'll write, I don't want to use exactly the same notation as Hoover, so I'll decorate it with a solid in the superscript with a map from R such that, so first of all, G becomes invertible. in there. And the second thing is that Fi over G is power bounded in R for all I. So that kind of encodes the idea I was talking about with you want Fi over G to go to the closed unit disk. You want Gi to be invertible. So the proof is you can just construct the guy. So you can start with, well, you could first invert G, but I'd rather, maybe I'll do invert G at the end. So what you can do is you can take R and adjoin just polynomial variables x1 to xn, and then solidify with respect to all of them. Which, recall, does something when R is not discrete. Remember, we had the example of one variable and R was QP, then this gave us the Tate algebra. And then we can say that these variables are supposed to be Fi over G, so maybe Gxi minus F. So Gx1 minus F1, Gx2 minus F2, Gxn minus Fn. And then it doesn't matter at which point you invert G, but let's do it at the end. And this kind of obviously satisfies the correct universal property. So first we freely adjoined solid variables, and then we imposed the relations which guarantee that kind of thing. There's one small thing to check, which is that after you take this, in which these are definitely solid, and then you do these operations, you need to see it's still solid, but that's because it's all colimits. Okay. So this is the kind of thing you're looking at. And now I want to make a caution here. Yeah, no, exactly. So just a sec. So this is not exactly the value of the structure sheaf. On x, F1, Fn over G. It is pi 0 of the value of the structure sheaf.
So you want to have a derived structure sheaf.
Yes. So I said that this, when I was discussing this six-functor formalism and this localizing the category, I was always careful to say it was the derived category. And in fact, these things really only work, these six-functor formalisms and so on really only work at the derived level. And what that means is what you're producing a priori is a derived sheaf, not an ordinary sheaf. So that's, okay, but now I'll say, but in most practical cases, almost all practical cases, all pi I equals 0 for I bigger than 0. So in practice, it doesn't seem to cause trouble, but it's an important thing to keep in mind. And the second warning is so even if R is very nice, some kind of Huber ring, then this quotient may not be. So this may not be quasi-separated. So I
Okay, so it's a kind of a non-Hausdorff quotient of restricted formal series in general.
Yes, exactly. So this will always be this will always be the usual Tate algebra in many generators. That follows basically from the arguments we gave for any sort of Huber ring R. But then when you take this quotient, the ideal generated by these elements might not be closed. So in principle, you could be having a non-Hausdorff quotient here.
So you start, when you say Huber ring, you mean complete Huber ring?
Yes, I mean complete Huber ring. Thank you. Yes, yes. But again,
But this theory is defined for not necessarily complete Huber ring as well, or?
no, this theory is only defined for complete Huber rings. The theory I'm discussing.
Because you cannot define the condensed of any topological thing.
You could define it, but it won't be solid unless the thing is complete in general.
Ah, okay, you want solid, so you want complete.
Yeah.
And then the other guys, when you do this, it is still solid, but doesn't come from, it's kind of non-Hausdorff.
Yes, yes. Yeah, but again, in almost all practical cases, or maybe all practical cases, it is quasi-separated, i.e. Hausdorff. So what I was trying to aim for is the relation to Huber's theory. I guess I probably won't get there. I think we'll definitely discuss this more detail later, but just as a preview. So if R is a Huber ring, and don't worry if you don't know what that is, it's just a certain nice kind of topological ring that people use in non-Archimedean analysis. And let's say complete.
Pair. Huber pair or Huber?
No, just Huber. I'm just doing the rings now. I'm not doing the pairs. And if if the ideal generated by F1 up to Fn inside R is open, which is the condition that describes rational opens in the space of continuous valuations as opposed to the space of arbitrary valuations, then in this case, Huber defines the ring of functions here. And you could ask what the relationship is with this thing that comes from the solid theory. And this is the quasi-separification of this more generally defined thing that we have here. So the solid thing. Or maybe, for emphasis, I should maybe put the pi 0 as well. So you can get the Huber thing functorially from this more general thing, and in particular from our structure sheaf, but they're not necessarily equal in general, but in all practical cases, sort of they are equal. That's the general outline of the story.
So in general case, the thing is derived, or okay, you mentioned it's not. And so in general, if you always use derived structure sheaf, it doesn't always satisfy the descent.
Yes.
So it's always sheafy.
Yes. Yeah. So so maybe that's an important point to mention. There was this little fly in the ointment in Huber's theory that, in the general setting, he defined a structure sheaf, except it wasn't a sheaf; it was only a pre-sheaf. And in all practical cases, it was a sheaf, but still, it was a little bit. The general theory was kind of missing something for that reason. That's fixed by this. So if you no longer care about things being quasi-separated and non-derived, then you get a good plain old structure sheaf. And you get even more. You get derived category of quasi-coherent sheaves, which localizes, and also you get the possibility of defining all of these things even without this condition being present. Okay, I think probably I'll stop there. Thank you for your attention. Yes?
Do you have any use of non-continuous valuations?
Any use? Yes. I know Kolmez likes them. So he has this notion of ad hoc spaces, and those correspond to certain.
Yeah, but you don't really use them.
I think he used them.
No, but you.
Oh, me. Well, look, I just build the theory. I don't. He calls them ad hoc spaces. I don't think he developed the theory. He just kind of did it in an example. So he wanted to exactly include things like this open unit disk, kind of. So this, yeah, things like this ZP. I think in his paper where he does this GL2 mod P Langland. Is that right? You know, I don't know. So he wants to. This thing is a prototypical example of a topological ring that's not a Huber ring. So in the usual theories of rigid analytic geometry, the open unit disk, you can't think of it as an affine space because the ring that it corresponds to is not one of your allowed rings. So you always have to think of the open unit disk as a union of the closed unit disks contained in it. It's this non-quasi-compact thing to fit it inside Huber's theory. But Colmez advocates that sometimes it's better to just work with this thing as if it were affine, and that's something that our theory easily accommodates.
Yeah, there are people who did, I forgot the name of this, construct some notion of rigid, I forgot the name, there was some paper on this, I mean, like variant of I forgot the name of there was some paper some time ago, maybe, but I'm not sure. Okay.
Any other questions?
Yes.
Yes.
Does every solid Z algebra defines analytic structure?
So this notion of analytic ring, we haven't defined it yet. It kind of organizes a lot of discussion. But indeed, yeah, if you have an algebra in solid Z modules, you get what we call an induced analytic ring structure. So it's just you take all. I mean, I said the module category you have, and that sits inside condensed R modules, and that is an analytic ring. Yeah.
But in case of ZT, we had something like more natural analytic structure on the subcategory.
More natural. It's arguable. It's more complete. They're two things. They exist. They do. Yeah. I mean, you want them both, I think.
And this can be extended to any discrete ring, right?
Yes, that's right. Yeah.
Not in general, not general solid Z algebra.
Well, for a general solid Z algebra, I don't necessarily know of any like completely canonical. Well, like maybe, I mean, one thing you could do is you could take all of the power-bounded elements and force all of them to be solid. That would be kind of the maximally complete thing that you can get via the stuff that we've developed. Yeah. But there could be further completions of that, as far as I know. I mean, yeah. You're welcome. Yes.
With the definition of solid analytic rings we used in the very first lecture, if we use this instead of a regular ring here, do we get something similar to like Huber's theory for Huber pairs instead of just regular rings?
Could you repeat the question? I'm not sure I understood it.
In the very first lecture, we defined like solid
analytic rings, solid analytic rings. Yes.
Pairs with the ring and the derived category. If we try applying something similar here to analytic rings.
What do you mean? What do you mean? You mean like this discussion of this thing here? Oh yeah. You can do that. Yeah.
But do we recover like?
Oh yeah, you recover the theory of with the R plus in there as well. Yeah.
So elements of R plus you require solidity for.
Exactly.
Not for all of the guys.
Exactly. So you can yeah, and we will discuss this. You can add that extra flexibility into the picture. Yeah.
And the fact that R00 is this is automatic. That those are the topologically important ones are automatic.
They're automatically solid. Exactly. Yes. Okay. Yeah. So it actually fits remarkably well with Huber's theory.
And in the previous theory, like you take tensor product of analytic ring, you have to first like solidify one direction and then another. You have to take colimit of the.
Yeah. Usually. Yeah.
So here it's still the same.
Here you don't have. Well, these solidifications all commute with each other. So there you don't need to. Yeah. They're all given by R Hamming out of something, and any two R-humming out-ofs commute with each other. Yeah. Other questions? Okay, well, see you on Friday or next Wednesday or whenever.